Welcome to your How Neural Networks Think preparation session. Today we are diving deep into the mechanics of deep learning, and by the end of this lesson, you are going to walk away with complete clarity on this topic. So let's get started. Have you ever wondered how a computer can recognize your face or translate languages instantly? It all comes down to neural networks. These systems are inspired by the human brain, consisting of layers of interconnected processing units. By passing data through these layers, the network learns to identify incredibly complex patterns. It doesn't do this by magic, but through iterative mathematical adjustments. This process forms the absolute bedrock of modern artificial intelligence. Over the next few minutes, we will demystify exactly how these networks process information, adjust their parameters, and ultimately think. Let's look at the fundamental building block of any neural network, the artificial neuron. Think of it as a tiny decision-making machine. First, we have the inputs, labeled here as x1 and x2. Each input is multiplied by a specific weight, which determines how much influence that input has on the final decision, much like how some factors in your daily choices carry more importance than others. Next, we add a bias term, labeled b. The bias allows the neuron to shift its activation threshold up or down, giving the system more flexibility to adapt to different scenarios. All of these weighted inputs and the bias are then added together at the summation node. This combined value, which we call z, is passed directly into an activation function. This function acts like a mathematical filter, deciding whether the neuron should fire and determining its final output value, which is then sent downstream to the next layer of our network. Now that we understand the visual structure, let's look at the exact mathematics behind a single neuron's calculation. Don't worry, it is quite straightforward. First, we start with our general formula. The weighted sum, z, is equal to the sum of each input multiplied by its corresponding weight, plus the bias. Let's plug in our specific values. We have inputs of 2.0 and 1.5, weights of 0.5 and -1.2, and a bias of 0.3. Next, we simplify the multiplication steps. This gives us 1.0 minus 1.8, plus our bias of 0.3. Finally, we add these numbers together to get our result. The final weighted sum is -0.5. This value is what gets sent to the activation function. Why do we need activation functions in the first place? Without them, a neural network is just a giant linear equation, meaning it could never learn complex, nonlinear patterns like images or text. Let's compare the three most common activation functions you will encounter. First, we have the sigmoid function. It squashes any input value into a tight range between 0 and 1. This makes it perfect for binary classification, where we need a probability output. Next is the rectified linear unit, or ReLU. ReLU is incredibly simple. If the input is negative, it outputs 0. Otherwise, it passes the input through. It is the default choice for hidden layers because it is computationally efficient. Finally, we have tan, or hyperbolic tangent. It maps inputs between -1 and +1, which helps center the data around 0. Imagine standing on a rugged mountain range in thick fog, trying to find the absolute lowest point. This is exactly what a neural network does when it tries to learn. We call this mathematical terrain the loss landscape. The height of the land represents the network's error, or loss. Our ultimate goal is to find the deepest valley, which represents the global minimum where the network's predictions are highly accurate. If the network makes poor predictions, it sits high up on a steep ridge. To navigate down, the network calculates the slope of the ground beneath its feet. It then takes a step in the steepest downward direction, a process known as gradient descent. This visual representation helps us understand why training can sometimes get stuck in shallow valleys, which we call local minima, instead of reaching the true bottom, or why too large of a step might cause us to overshoot the valley entirely. To understand how a network actually learns, we must look at the continuous loop of training. This loop consists of two main phases, the forward pass and the backward pass. First, input data enters the network and moves forward through the layers. The network makes a prediction based on its current weights and biases. Next, we compare this prediction to the actual target value to calculate the loss. This loss tells us exactly how wrong the network's guess was. Once we have the loss, we initiate the backward pass, also known as backpropagation. We send the error signal backward through the network to calculate how much each weight contributed to the mistake. Finally, we update the weights and biases using an optimization algorithm. This cycle repeats thousands of times until the network becomes highly accurate. Let's look at the actual mathematical formula that updates a weight during backpropagation. This is the heart of gradient descent. First, we state the standard weight update rule. The new weight is equal to the old weight minus the learning rate, represented by eta, multiplied by the gradient of the loss with respect to that weight. Now, let's plug in our numbers. Our current weight is 0.8, our learning rate is 0.1, and our gradient is 0.4. Next, we calculate the step size by multiplying the learning rate and the gradient. This gives us 0.04. Finally, we subtract this step size from our old weight. Our updated weight is 0.76. By making this tiny adjustment, we have successfully nudged the network one step closer to making better predictions. Let's test your understanding of what we have covered so far with a quick question. Which activation function is most commonly used in the hidden layers of modern deep neural networks? Option A suggests the sigmoid function, which squashes values between 0 and 1. Option B proposes the rectified linear unit, or ReLU, which outputs 0 for negative values and passes positive values through. And option C suggests the tan function, which maps values between -1 and +1. Take a moment to think about which one is the standard choice for hidden layers. The correct answer is B, ReLU. ReLU is widely preferred for hidden layers because its simple mathematical nature prevents training slowdowns and avoids the vanishing gradient problem that often plagues sigmoid and tan functions. Before we wrap up, let's do a quick active recall session to lock these key concepts into your long-term memory. First, what parameters act as the strength of connections between neurons? Think about it for a second. The answer is weights. Weights scale the input signal and determine how much influence one neuron has on the next. Next, which process calculates gradients by moving backward through the network? Give it a guess. The answer is backpropagation. This is the core algorithm that calculates how to adjust parameters to reduce overall error. Finally, what parameter allows a neuron to shift its activation function up or down? The answer is bias. Bias provides the necessary offset to ensure neurons can activate even when inputs are 0. Great job on completing these flashcards. Let's summarize the key concepts we have explored today. First, weights and biases are the fundamental parameters that define a network's knowledge and set its decision thresholds. Without them, the network cannot store what it has learned, and it remains completely unable to adapt to new data. Second, activation functions are crucial because they introduce nonlinearity, allowing the network to learn complex real-world patterns rather than just simple straight lines, which is essential for solving real-world problems. Finally, backpropagation is the engine of learning, calculating errors to guide gradient descent optimization step by step down the loss landscape. And that wraps up everything you need to know about how neural networks think for your deep learning journey. In our next class, we will be moving on to convolutional neural networks for image recognition. So make sure you stay tuned. Visit Examiverse AI Studio to automate your training modules.